Good morning and welcome to WEP on Air. My name is Michelle Ponto. I'm from the KAUST Communications Department and I'm here today with Leslie Dewan. She's the co-founder and chief executive officer of Transatomic Power, a nuclear reactor design company based in Cambridge, Massachusetts. She received her PhD in nuclear engineering from MIT and also holds a Bachelor of Science degree from MIT in mechanical engineering and nuclear engineering. She's a member of the MIT Corporation, MIT's Board of Trustees, and was named Time Magazine's 30 People Under 30 Changing the World. Welcome to our show this morning, Leslie.
Thank you so much, Michelle. It's really wonderful to be here.
This is your first time in the kingdom?
It is, yes. I just arrived day before yesterday, and it's been just wonderful being here.
And I know you already saw a little bit of Jeddah last night when you had arrived.
Yes, yeah, I was able to go see some spots of old Jeddah town yesterday and just see some of the amazing architecture that's around here, the old architecture and the new as well.
Well, we're so glad you can join us.
Thank you.
So we're going to talk a little bit today about nuclear power. Actually, we're going to talk a lot about nuclear power today. And I know it's sometimes a controversial topic, but you don't see it that way. You have found a new way of doing nuclear power that could change the world. Tell us what's a little bit different about your reactor.
With Transatomic and our new reactor design, we're trying to figure out a way to address the four big issues facing nuclear power, the issues of safety and waste and proliferation and cost. And it's only by addressing those four issues can you make a type of nuclear reactor that people will want to have, that will make sense for the environment, sense on a human level, in addition to making technological sense. So we developed a slightly different type of nuclear reactor design that actually uses liquid fuel rather than solid fuel. And that alleviates a lot of the safety concerns that face some of the traditional nuclear reactors, and in parallel with that can help address the waste, proliferation, and cost concerns as well.
So when you say liquid fuel, is that the molten salt that I've been reading about in your research?
Yes, it's a molten lithium fluoride, uranium fluoride salt.
Okay. And I know that has been around since the 1960s, or at least people have been experimenting with it since the 1960s. What was it that made you go back to that knowledge from that time?
So the 1950s, 1960s, at the very beginning of the nuclear industry, there was like a real sense of blue sky thinking about the technology. People were pursuing all sorts of reactor designs that would, in some respects, seem crazy today. So they were looking at the liquid-fueled reactors. Those were when those were first developed and prototyped, looking at gas-cooled reactors, looking at nuclear-powered cars, looking at nuclear-powered airplanes. And so back in the 50s and 60s, researchers at the Oak Ridge National Lab in the US developed and built the first prototype molten salt reactor. And they showed that it worked. They showed that it had tremendous safety benefits, that in effect it couldn't melt down, even in the worst case scenario accident. The problem was the reactor back then was very expensive. It had a low power density. There were some materials issues that just made it not immediately commercializable. It required very highly enriched uranium as fuel, which was, again, a little bit problematic. And no one really cared so much about the safety benefits, because when they built the prototype, it was in the mid to late 1960s. It was before there had been any significant nuclear accidents before. So they said, well, why would we pay 2 or 3 times as much for a safer nuclear reactor when we don't need one? So what my company was able to do was look at that original design and figure out a way to make it more compact and power dense and therefore lower cost, while keeping the same safety benefits of the original design.
Okay. So back to my question, because you studied nuclear, so you were definitely into changing the world at that time. Why go back to the molten salt when you could maybe work on what's currently out there and try to make that safer? Why was the molten salt still of more interest to you?
We felt like there were a lot of benefits by going back to that earlier part of the technology tree and just try something that's completely different from the reactors that we have today. Because the light water reactors that we have today, they work and they work very well, but there are limitations with them, and we feel that if you can go to a different fuel form, try something just very revolutionary, you're able to solve a lot of the safety issues there.
And what has changed in the last, I guess it's been 50 years since the first reactor was built, the molten salt one. And at that time you said it was too expensive, the current models were much cheaper. What has changed to make these now viable?
So there are two main things that changed. So one of them is there are different materials that are available today and have a much more robust supply chain today. So for example, steels that can withstand corrosion at very high temperatures, or metallic composite materials and ceramics that similarly can go up to the very high temperatures that these molten salt reactors need and last for a long period of time, can last for decades without breaking down. And then the other piece in parallel with the materials development is just modern computational techniques. So when they were first looking at these in the 50s and 60s, they would have to do effectively hand calculations to figure out what geometries you would have for your reactor, what the neutronics would look like, what the flow patterns in the reactor would look like. And now where you can run hundreds of simulations, thousands of simulations on a high-performance computing cluster and very readily hone in on the optimized geometry for the reactor core and the heat exchangers and the primary vessel piping. So better materials and computer techniques.
Okay, you touched on a little bit that your reactor doesn't produce the same nuclear waste as the current reactors do. Does it produce any kind of waste?
It does. So we're able to get twice the fuel utilization of existing nuclear reactors, and we therefore leave behind just under half the waste for a given amount of power produced. So we haven't solved the nuclear waste problem, but we're making progress in that direction. So basically we have twice the mileage of an existing nuclear reactor.
Okay. So there's already a lot of nuclear reactors out in the world. Is it possible to use your technology in the existing ones, or do you have to build completely new ones?
So yeah, unfortunately we can't retrofit the existing designs because they're just too different technology-wise. So they have the different fuel, different coolants, and they operate at very different temperatures. So it would be not cost effective even to reuse the turbines. At best, you could maybe reuse like the switch yards and the connections to the transmission lines within the reactor, but they would require new construction.
Okay. Is there a risk of, if you went to the molten fuel, of maybe exhausting that fuel to make this new fuel of nuclear energy?
Oh, so that's actually a really interesting question. So there aren't very good estimates currently of what worldwide uranium reserves are. So there isn't really a good sense of like, well, how many decades, how many hundreds of years worth of uranium fuel do we have? But one of the nice things about molten salt reactors is that you can use types of fuel with them other than uranium. So in addition to uranium, you can use thorium fuel in different types of molten salt reactors as well, which would greatly extend the amount of fuel, the amount of power that you could get out of it. We're not working on a thorium fueled design, we're working on the uranium fueled design, but there are a lot of parallels between the two technologies.
Okay. One of the things with nuclear, when people say, oh, we're going to put a nuclear plant in your area, the first thing that comes to mind is devastation. We're all going to end up with cancer. If it melts down, bad things are going to happen to us. You said yours is much safer. How safe is it?
So this reactor, there are two main factors that keep it safer. So one is that it operates at atmospheric pressure rather than the hundreds of times atmospheric pressure of a conventional reactor. So you don't have that large driving force that could potentially push radioactive material beyond the site boundary in the event of an accident. And then the other factor is even more directly tied to the liquid fuel itself. So if the reactor shuts down, if you lose external electric power, for example, the molten fuel freezes solid. It freezes when it gets below about 490 degrees Celsius. And at that point, if it fails in a solid mode rather than in a liquid or gaseous mode, so it's self-contained more than fuel that starts out as solid and then when it goes into a meltdown it becomes liquid or has volatile gas products coming off of it.
Okay. When I was doing my research before the interview, I noticed that the U.S. really hasn't built any more new reactors since the 1970s. Is that because they don't need them, or is it because they're trying to use alternative energy, or because they are afraid of nuclear energy?
I think it's kind of all of those factors combined. So right now in the US, there are 5 nuclear power plants currently under construction, 99 currently operating, but those plants have had substantial cost overruns. And so I think that to first order in the US, a lot of the pullback from nuclear power has been due to the rising costs and the cost overruns, and especially in parallel with the very cheap natural gas prices in the US and the falling prices of renewables, especially solar. Mm-hmm. And so if there isn't an economic incentive there, there really isn't any pull for developing the new technology or for building the new technology.
Okay. So where do you see your new reactors going? Where, if the U.S. doesn't have that economic pull, which areas do have that pull, that are needed, or that will be looking for this kind of stuff?
Well, partly, I think, and this is a long way off, so it's very premature for me to give cost estimates, but ultimately, I think that the advanced reactors are only going to matter if you can make them cheaper than coal, if you can make the cost be as close as possible to natural gas, because you need those economic incentives, and you want those economic incentives to be in line with what's good for the environment. And so I want us to have nuclear reactors that are cheaper than coal, and that we'd be able to replace the coal power plants coming offline in the US with these newer, safer reactors. And then in parallel with that, I think there's a lot of market for newer, safer reactors in rapidly developing countries. I think China, India, Brazil in particular, Saudi Arabia, ideally countries that see a rising need in electric power demand.
Do you see the balance between cost, environment, one of the things that keeps going up and down? We want to do good for the environment, but it costs too much. We need to do this, and is that one of the reasons why certain energies are not being embraced as quickly as they should be?
I don't think so, actually. At least in the nuclear sector, I don't think you see that trade-off, because, I mean, honestly, in part, with the advanced reactors, they're in such an early stage of the development, so it's not at a point where we can say, it's the baseline design isn't developed yet, so there isn't really a point at which you can say oh, well, if you cut that corner, it would be so much cheaper. It's just we're trying to develop what the baseline design is first. Mm-hmm. And so I think a lot of it just comes down to, if you get technology that's very inherently safe, the lower cost can go hand in hand with that. I think a lot of the higher cost of the conventional nuclear reactors are the backup safety systems that are necessary there. For example, the containment dome for a conventional light water reactor is about 25% of the cost of the plant. So if you have a design that operates at atmospheric pressure, you don't need a dome that's as substantial or as expensive as that.
Okay. I'm originally from Canada, and I know where we have our nuclear power, the water is a little bit warmer in that area. Is that something that also happens with your reactor? I'm just thinking of the Red Sea, because it's already really warm, and if we made it warmer, that would probably be bad for the things living in there. Does yours put off the same kind of heat, or does it work differently?
Oh, yeah, that's a really good question. And so that actually comes down to what type of power production cycle you end up using with the nuclear reactor. So if you have, so basically all of the light water reactors today, I believe worldwide, certainly all the ones in the US and Canada, just have a typical steam cycle on the back, and they have to use a body of water as the lower temperature heat sink. And so there's no radiation interface with that body of water, but you are putting out, you're sinking a lot of heat into that body of water. Some of the advanced nuclear reactors can be air-cooled, so you don't have to use a body of water as a heat sink, and that also opens up a large number of different siting locations. Though that's totally separate from the nuclear development side of things, but it's something that would greatly widen the range of areas where you could have one of these reactors.
Okay. As a scientist, obviously you believe in what you're producing and what you're making. How do you go about convincing people or industry or policymakers to embrace your new concept?
I think lot of it comes down to being able to communicate about what the technology is and what the benefits are and what the costs are, and kind of let people make the decisions for themselves on the basis of that information. Like partly I don't want to push too hard. I kind of just want to present the information in an open and transparent manner, and then just see where the technology falls in comparison to the fossil fuels that are available, and the solar and wind and hydro and geothermal that's available as well.
Okay. What kind of challenges have you faced producing this? I know that obviously there's, you have theories and sometimes they don't work. How many prototypes or how many renditions have you gone through so far to get to the reactor that you're working on today?
So we're just at the lab scale testing phase right now, just doing, well, primarily computer simulations and then lab scale tests of corrosion and some radiation damage testing, and very, very early stage. But despite that, we have had to go through some iterations of the design as we honed in on how it was going to actually work, as we corrected errors that we made in the early phase of the design, and as we figured out basically the best way to move forward with a safer reactor design.
How different does it look compared to the one from the early 1960s?
So it's, we use a slightly different type of fuel salt. We use a different type of moderator within the reactor as well. The core is more power dense, so it's physically quite a bit smaller. The prototype in the 1960s, it wasn't connected to a power production cycle, so a lot of what we've been doing is sort of optimizing the flow within the primary loop of the reactor, the heat exchanger design, so you can best connect it to a power cycle.
Okay. And it's not ready yet for use. When do you think it will be ready for people to start building the plants?
So it's going to be a very, very long road. So ideally, and I'm almost hesitant to give timing estimates because it's so far out from now, but we ideally want to break ground on a prototype facility in the early 2020s. And then we have to build the prototype facility, operate the prototype facility, and only then, after we have multiple years of operating data from the prototype facility, would we then be able to move on to start developing the commercial scale reactor design.
But that's still exciting. That 2020 is not that far away. It's only
early 2020s. Yeah, not 2020.
It's still exciting. It must be nice to be able to see progress with your work.
Yeah, it's a really exciting industry to be in, especially because now there are several dozen advanced reactor developers worldwide, just many, many advanced reactor development design efforts, well, from startups, from universities, from national labs, all over the world. So there's this growing community of people who are just trying to solve similar problems, like kind of working with one another on addressing supply chain issues, on figuring out viable regulatory pathways, figuring out what the market will look like 10, 20, 30 years from now, and solving those hard problems together.
Do you think the dreams of the 60s will come true, the nuclear-powered car and those kind of things? On some level, I hope so. I mean, a nuclear-powered car clearly has some issues involved in it, but nuclear-powered cargo ships, or just a greater share of nuclear-powered carbon-free electricity, or just more carbon-free electricity. Okay.
Yeah. Right now in the U.S., 2/3 of our carbon-free electricity comes from nuclear power, so it's really doing a lot of the heavy lifting there. And I think as the world, develops the electric grid of the future, the electric production portfolio of the future, I think that we're going to see a lot of nuclear and a lot of solar and wind as well.
Okay. I'm going to take it to questions from the audience and our virtual audience.
We have a question from Khalid online, who is interested in the safety aspect of nuclear power. Maybe you could talk a little bit about the safety status of the nuclear plants that are generally in operation now, whether
Oh,
or
yeah.
not they are safe, and maybe compare them a little bit more. I know you've spoken about it already, but with the type of plant that you are advocating.
Absolutely. And also, I just want to say at 12:30 local time, do I look in that camera or do I look at you? Sorry. Sorry about that. Oh, perfect. Thank you very much. So at 12:30 local time, I'm going to give a more technical lecture because I realized that I was not getting into the technical aspects of this at all here. But so to answer your question about safety of the existing fleet of nuclear reactors and how that compares to the new designs, the current nuclear reactors, the light water reactors, are actually the safest form of power generation that exists. So if you just look at the raw numbers of, I mean, it's a bit blunt to say this, of deaths per terawatt hour of power produced, you see coal power production is, I think, around 4,000 deaths per terawatt hour. Wind and solar are ballpark, I think, around 40 or 50 deaths per terawatt hour. Those are people, you know, falling off roofs, putting up solar panels, for example, or dying while working on wind turbines. Nuclear power, I believe, is 0.4 deaths per terawatt hour. And it's, again, it's a little bit blunt to put it in terms like that, but I think that we should, it's important to think about it that way and to analyze it that way. I think that a lot of the fears surrounding nuclear power is that when there's a nuclear accident, the repercussions spread beyond the site boundary. And so you can say, you know, a nuclear accident anywhere is a nuclear accident everywhere. And so it spreads a lot of fear. And that's something that it's real, and it's, you know, it's important to address that, but I think that we should be mindful of you know, where it falls numerically in the scale of things. And the main difference between the accidents that can happen with the existing light water reactor fleet and the newer generation of accidents is if there's an accident, it's confined to the site because it operates at atmospheric pressure, so there's, again, no force to push it beyond the site boundary. So accidents are still possible. Nothing is completely accident-proof, but it's localized.
Leslie, it appears that you started your company 3 years before you finished your PhD while you were still a student at MIT. Can you describe sort of how that happened and the ramp-up curve in terms of your own effort and the growth of the company? I'm sure there are a lot of doctoral candidates within the scope of your voice right now that are incredibly curious about how, you know, you created a company while you were doing your doctoral research and got, you know, investors and other people to believe along the way. Who were the principals involved? Was MIT supportive? Was it your advisor? Or was this really something that you did on weekends? just describe the drama of creating a company for us.
Oh, absolutely. Yeah, those last few years kind of passed in a blur. Yeah, so we incorporated the company in 2011, and I graduated with my PhD in 2013. So there was 2 years when it was completely overlapped, and the work for developing this reactor was completely separate from my PhD thesis research. So it was, you know, work on my PhD research for, you know, most of the day into the evening, and then any hours remaining, there's sort of a titration involved. But it was, you know, even though the technical basis was completely, there wasn't any technology overlap, the two projects sort of like fed on one another. And as I became more excited about my thesis research, it just gave me more drive to, you know, work on this company and develop this further as well. It was a very busy time, but very fun.
Are you permitted to disclose any of your investors in the sense, like, do you have any big energy companies that are part of the portfolio, or is it all, you know, venture kind of people that you've gotten along?
So we're venture-backed. Our main investor is Peter Thiel's Founders Fund, which is based out of San Francisco, and they're absolutely wonderful to work with. So in the early days, when, you know, I was still in grad school, trying to find an investor, you know, a first investor to lead our first round, we talked to a lot of VCs who were kind of more familiar with investing in software companies, for example, and we'd pitch them on the technology and say, this is amazing, and you know, they'd agree, and they were like, this is wonderful technology, can we have a reactor in 6 months? And we said, well, no, it's going to be 10 years. Like, best case scenario, it's going to be 10 years. And you know, Founders Fund, because they were one of the big early investors in Elon Musk's SpaceX, they had a sense of, you know, what it means to work on, you know, hard technologies that unfold on very long timescales, on multi-decade timescales. And also they had a picture of the nuclear-powered airplane on their website at the time, so we knew that they were kindred spirits.
May I be permitted one more?
Yes.
So, you referred often in your discussion this morning to the relevance of simulations in advancing the designs, something that is different, of course, from the 1950s when we had just a few kilobytes on computers, and you know, now every 10 years we get a factor of 1,000 improvement in computer performance. Are you actually running on DOE's largest systems now, or what is sort of the scale of the engineering simulations that your company's working on?
So we're, right now we're not using any of the high performance computing clusters within the US National Lab System, but we, over the past year, we were working on a longer time horizon project with the Oak Ridge National Lab, and they were, I'm actually not sure what clusters they were running it on. It wasn't, those simulations weren't the incredibly computationally intensive ones, but we were, able to have a grant to use DOE resources there.
And it's mostly material science simulations at this point, as opposed to fluid thermal, you know, transfers and so forth? Or?
Those ones that we were running before were neutronic simulations, and there's some thermal hydraulic simulations that are being run right now. And one of the really interesting fields, though this is still being developed for the liquid fuel molten salt reactor technology, is like better multi-physics modeling. So things that couple the neutronics and the thermal hydraulics, and they're about, I think, like 4 or 5 different groups that are working on developing new models for that, and so it's wonderful seeing that come to fruition. And then beyond that, my wish list is that people will figure out better computational techniques for corrosion simulation, because that would make my life so much easier.
Well, fascinating horizon. Thank you very much.
Thank you.
I have a question about the investors that you got at the beginning, because I know a lot of our students and even a lot of those watching are entrepreneurs. How did you get them? Do you think being in the MIT area helped, or would it matter? Like, what made you stand out among everybody else who's approaching these people for funds?
That's a really good question, actually. I should probably at some point ask them, because honestly, I think it's a mix of, they liked the technology, and they, you know, so one of the great things about Founders Fund, and this is true of a lot of our other investors as well, is that they have a serious nuclear engineering or nuclear physics background. So Founders Fund has a chief science officer who has a PhD in nuclear physics, for example, and so they were able to look at the technology and really understand it and see what was going on there. And I think that's an important factor for this type of like hard technology, longer time horizon investments. You have to dig really deep into the technology itself and sort of have that understanding there.
Okay. Did you find them, or did they find you? How did they learn about your research?
I'm honestly not sure, because it was so many years ago. Not so many years ago, like 4 years ago. This sounds likely, but I might actually have this wrong. I think that we reached out to them at one point, and then we didn't hear back from them for a very long period of time. And then out of the blue, they reached out to us again. And I'm not sure whether those two messages ever, I'm not sure whether they even saw our first message. So it was sort of a mutual first introduction there.
That's interesting. I'm always curious on how these things kind of happen, the synergy on little connections from the past that will make things into the future if based on, because obviously you were still doing research, you were probably still promoting it through whatever channels you could. You had done the reach out, but it took years before they actually came back. So it's nice, it's a nice story of never kind of giving up, and you never know what will happen.
Yeah, it was definitely a long time horizon process, and yeah, I mean, a tough process finding investors who were, you know, especially 4 years ago, who were interested in this type of technology. Like now, it's a much better developed sector, or it, you know, it exists as a sector, and there are base cases, and there's a sense of like of what works and what does not work. But then it was so new. We felt like we were really just heading out into the unknown, and we had plenty of people who were telling us that we were completely insane for approaching it.
That's interesting. So obviously you approach more than one investor, so it is kind of like even when you're submitting papers to a journal, usually it's the first time it doesn't always happen, but you have to be patient and keep looking, keep applying, keep asking.
Oh yeah, it was probably 24 investors that we talked to.
Okay. That's good for people to hear that it doesn't happen easily. You do have to work at it.
Oh yeah.
Yeah. Any other questions?
Yes, two of our viewers online, Annie and Zafar, are asking a similar question. I'm sure you've heard it before. Why should we invest in new nuclear plants, even more efficient and more safe nuclear plants, rather than investing in renewable energy resources?
Oh, I really like that question a lot. And the answer is that we need to do both. We need to have a broad and diverse energy portfolio if we want the grid to be robust, no matter what country that we're building it in. And to get a bit more specific, what nuclear is very good at is developing baseload, or is providing baseload electric power. So sort of always on, like, bottom part of the demand curve. Solar and wind, in particular, are good at doing peaking, for example, especially if it's in conjunction with very good methods of storage. But it's always helpful to have an always-on baseload, and that's what nuclear can provide.
I have a question about what happens with the spent nuclear fuel in your reactor. You noted that it was more efficient and you can get more mileage out of it, for instance. But one of the dangers of existing nuclear waste, I suppose, is proliferation, possible nefarious purposes that it would be put to use for. What about your type of reactor? How does that compare with the conventional light water reactor waste that we have now?
So our, like the isotopic profile of our waste is very, very similar to what's produced by a conventional nuclear reactor. We just have less of it, slightly less than half for a given amount of power produced. So you do still have to address those concerns of how do you store it over long time scales, into the tens of thousands of years, hundreds of thousands of years. It's going to be around for a very long time. And so I think a very rich and fruitful area of research is figuring out not just storage techniques for the waste, but different ways of utilizing it. And it's not something that our reactor can directly utilize, but I think that's an especially interesting area to me for nuclear engineers going forward.
That is interesting to see it as a way of maybe it's not waste, maybe it's useful in some other way.
Yeah, and that's what, I mean, when we started the company, we thought that we were able to directly consume nuclear waste, and one of the big design revisions that we had to make was when we realized that our initial calculations were wrong and we weren't able to directly consume the nuclear waste. And so that was, I mean, that was a tough realization to come to, because for me personally, that was the exact problem that I wanted to be solving. But I think that there's still some very intriguing possibilities out there, and I think if I had to urge other young nuclear engineers to work on a particular problem, I think that's exactly the one to go for. I think that's really the crux of a lot of it.
Yeah, that would have been devastating. That would have made a good movie of. Yeah, I can just imagine, because you had to totally change gears and you still kept on with the dream, and now you have something new coming out.
Yeah.
Yeah. Any other questions?
We have one question here. I'm not sure how you'll be able to speak to it. If you have knowledge about the energy market in South America, Samir is asking, are there projects to impact the energy market in South America? And what kind of obstacles have they found to impact this market?
Ooh.
Do you know anything about South African energy in particular? South American.
I'm not sure, actually. I know that, I apologize, I might be a little bit too ignorant to do this. I mean, there are nuclear power facilities in Brazil and I believe in Argentina as well, but it's a fairly small share of the market. I know there's very good hydro in a large number of South American countries. And since hydro is very good, carbon-free baseload to some degree, that obviates the need for substantial nuclear investment. But beyond that, I don't really know. I apologize.
How portable is nuclear energy? Is it possible to export it to some of these places where they can't have their own plant?
Like make a small modular design that you could ship over there.
Yeah.
Yeah, that's not something that Transatomic is working on specifically, but or there are like a few side projects that we think would be really interesting. But there are a number of other advanced nuclear startups that are working on projects along those lines. So like say you can make a very, very small nuclear reactor that you put in a shipping container, for example, and then you could bring that to you could export that to other countries. You want to make sure that it's very, tamper resistant basically, so you don't have proliferation concerns. But yeah, those could be useful for remote regions where the cost of electricity is very, very expensive. And you could also use them for bringing power to disaster-stricken areas. For example, like after the hurricane in Puerto Rico, for example, you bring in a small modular nuclear reactor, use it to power the area, provide baseload power as industry is ramping up again, as people are rebuilding, and then bring it out once you don't need it anymore.
Oh, that would be
or
great.
leave it if people want that in their backyards, which they might.
They might. Interesting. Any other questions? No? Well, thank you for joining us today, Leslie.
Thank you so much for having me.
Oh, it's been great. And if you want to know more about nuclear energy, please tune in at 12:30 today. You'll be talking a little bit more in depth. You said more technical.
Yep. Yeah, I have 45 minutes or an hour and slides and graphs, and it'll actually get into what the technology is.
Okay. So if you want more details, come back at 12:30. We'll be streaming that one live as well. Thank you very much. Thanks for joining us.
Thank you.